Okay. Hello, everybody, and welcome to a new session of our webinar, AmSur on differential geometry. First, let me recall you that in the chat you can see all the links to our YouTube channel, the link to the WhatsApp mail list, and other things. You can join us clicking on those links. And today, well, it is a great pleasure for me to introduce a former PhD student of mine, Alejandro Tolcachier from Córdoba, and who will speak about complex solvmanifolds with holomorphically trivial canonical bundle. Okay, thank you, Alejandro.
Okay, thank you, Adrián, for the presentation, and thank you for the organizers, for the invitation. As Adrián said, I will speak about complex solvmanifolds with holomorphically trivial canonical bundle. And this is based on a joint work with Adrián last year. So I'll start with some motivation. We begin by defining complex manifolds. An almost complex structure on a smooth manifold will be an endomorphism of tangent bundle such that at any point its square is minus the identity, and this implies that the dimension of the manifold is even. When this almost complex structure satisfies that the naive tensor defined in terms of J and the D bracket vanishes, we say that this almost complex structure is integrable, or we simply call it a complex structure on the manifold. And we have this very nice theorem due to Newlander-Nirenberg in the 50s that the real smooth manifold admits a complex structure, which is an pure algebraic condition, if and only if the manifold is a complex manifold, in the sense that there exists an atlas of holomorphic charts with holomorphic transition functions. In this context, if we want to study Riemannian geometry, the best metrics compatible are called Hermitian and satisfy that the J is orthogonal respect to the metric, or equivalently due to the square of J is equal to minus the identity, J is skew symmetric. And in this case, we can define a two-form omega in terms of J and G, and this form called the fundamental form of the Hermitian manifold. Okay, and well, which are the best or the most celebrated class of Hermitian manifolds are given by the Kähler manifolds, in which this two-form is closed. And these manifolds have two nice properties. For instance, the J is parallel with respect to the Levi-Civita connection of G, and therefore the Riemannian holonomy group is contained in UN. When the holonomy group is not contained only in UN, but also in SUN, the manifolds are called Calabi-Yau and have also very nice properties. For instance, they are Ricci flat. And when M is compact, there is an equivalence. The Riemannian holonomy group is contained in SUN if and only if the manifold is scalar, and there exists an N0 form, which is non-zero but closed. Okay, so now we are interested in studying the second condition. So I will introduce the main object of the talk, which is the canonical bundle of a complex manifold. Let's start with a complex manifold of complex dimension n. So we can define its canonical bundle as the n exterior power of the holomorphic cotangent bundle. And it turns out that this is a holomorphic line bundle, so a range 1. And okay, we can identify holomorphic sections of this bundle, which are called holomorphic n forms with n0 forms such that they are closed respect to the del bar operator in complex geometry. So what do we mean by holomorphically trivial is that there exists an over-vanishing holomorphic n0 form defined on the complex manifold. This is a trivializing section of the canonical bundle. So we will study this condition of the triviality of the canonical bundle. And okay, since the complex dimension is n, being del bar closed is the same as being simply closed. And with this definition, Calabi-Yau manifolds are simply compact Kähler manifolds with holomorphically trivial canonical bundle. And from now on, I will omit the word holomorphically just for shortness, but I will always mean holomorphically trivial canonical bundle. And well, recently there has been a lot of interest, not only in Calabi-Yau, but also in what is called a non-Kähler Calabi-Yau manifolds, because they are important objects in string theory and also in algebraic geometry. Okay, I will review some well-known examples of compact complex manifolds with trivial canonical bundle and also some facts. The first example would be complex parallelizable manifolds, which do a very nice result by Wang. They are compact quotients of complex Lie groups, and they have trivial canonical bundle since, well, the holomorphic tangent bundle, it can be identified with the T10 bundle, and it is trivial because it's complex parallelizable. So of course the n exterior power is also trivial. So these complex parallelizable manifolds have trivial canonical bundle. The only compact complex surfaces or complex dimension 2 with trivial canonical bundle are complex tori, K3 surfaces, or primary Kodaira surfaces. For instance, if you have an hyperkähler manifold, then the complex manifold with respect to J1, J2, or J3 has trivial canonical bundle. In a paper by Tosati, it is proved that the compact complex manifold has trivial canonical bundle if and only if it admits a Hermitian metric whose term connection has holonomy contained in SUN, and a well-known family of, and also yes, a well-known family which has a trivial canonical bundle are complex nilmanifolds due to Cavalcanti-Gualtieri and also by Verbitsky. And well, since I work on solvmanifolds, I will define first what are nilmanifolds. So nilmanifolds are compact quotients of simply connected nilpotent Lie groups by a discrete subgroups, which are called lattice. And well, here we want to study complex structure which are compatible with the structure. So a complex structure on the Lie group G is called left invariant if the left translations are holomorphic. And well, as usual, this is equivalent to have an endomorphism of the Lie algebra, which satisfies that the square is minus the identity and the corresponding nine-noise tensor vanishes. Okay, so a complex nilmanifold will be a nilmanifold equipped with an invariant complex structure. That is to say, this complex structure is induced by a left invariant one on the Lie group G. Well, so as I mentioned before, Verbitsky proved that there exists a left invariant holomorphic non-zero and zero form on any nilpotent Lie group simply connected. So any complex nilmanifold has trivial canonical bundle, and this is independent of the lattice. Okay, so a natural generalization would be to consider not complex nilmanifolds, but when the Lie group is solvable. So a solvable manifold will be a compact quotient of a simply connected solvable Lie group by a lattice. And similarly, a complex submanifold will be a solvmanifold equipped with an invariant complex structure. Some properties of solvmanifolds: if G has a lattice, then a necessary condition due to Milnor is that the group must be unimodular. This condition means that the operators in the Lie algebra have all zero trace. The fundamental group of the solvmanifold is isomorphic to the lattice, which we are quotienting, and also they are spherical, so the higher homotopy groups vanish. And we have this very nice theorem due to Mostow that if you have two solvmanifolds such that the lattices are isomorphic as groups, then the manifolds are diffeomorphic. So the isomorphic class of the group of the lattice determines the diffeomorphic class of the solvmanifold. But well, in contrast with the nilpotent case, where there is a criterion due to Malchev, there is no criteria to determine whether a given solvable Lie group admits lattices or not. So it's not easy in general to construct solvmanifolds. But in some cases, we have, for instance, this theorem due to Yamada. If we have a simply connected solvable Lie group of this form, an abelian part acting on the nil radical, we can say something about lattices. And the condition is that there exists a rational basis of the nil radical and a basis of Rk, such that in that basis, the differential of the action is a matrix in SNZ. So in this case, the Lie group has a lattice gamma, which has this form. So basically, we want to conjugate simultaneously the exponential of the, yeah, okay, well, I will talk about later in an example. But yes, we have a criterion to produce lattices in this case. Okay, so we want to study complex submanifolds with trivial canonical bundle. What about what is known? So there are complex submanifolds which admit an invariant trivializing section of the canonical bundle. A classification of the corresponding Lie algebras in the case of dimension 6 is given in this paper by Fino and Ugarte. Of course, also in contrast with the complex nilmanifolds, there are complex submanifolds whose canonical bundle is not trivial. For instance, Inoue surfaces, or more generally, Olje-Claus-Thoma manifolds. But what we showed with Adrián is that there are complex submanifolds whose canonical bundle is trivialized, but by a section which is not left invariant. So I will talk about these cases in this talk. But well, we can characterize which complex submanifold admit an invariant trivializing section. To do so, we need the Koszul-1 form, and we have this theorem. If we have a two-dimensional Lie group, not necessarily solvable, any Lie group with the left invariant complex structure, this Lie group admits a left invariant non-zero holomorphic and zero form, if and only if this one-form psi defined in terms of J and the operators add vanishes for all x in the Lie algebra. And in this case, any compact quotient will, by discrete subgroup, will have trivial canonical bundle. The sketch of the proof of this characterization, we start at the Lie algebra level because we have a left invariant complex structure. We take a basis adapted to this J, and then consider the dual basis and set this N0 nowhere vanishing form, which is wedging E1 plus I E2, and then all the others, since the okay, yeah, it's up to a constant is like the only N0 form. And well, we put the condition that the sigma is closed, and then we compute long computations, and we obtain this characterization above. This one form psi was introduced by Kosul in 1955, and it's called in many papers Kosul form. It was introduced in the context of G-invariant complex structures on homogeneous spaces. So we have this characterization of invariant sections, and with this characterization, for instance, we can recover some well-known facts or results in the literature. For instance, the complex parallelizable manifolds. We have that any complex Lie group satisfies that the trace of at Jx is equal to the trace of J at x, because the at x are by holomorphic. So, well, using the characterization, we recover that the complex parallelizable manifolds have trivial canonical bundle. Also for nilmanifolds, in the same paper by Verbitsky, they prove that an impotent Lie algebra satisfies that trace of J at x is 0, and the other term is 0 because it is unimodular. So also have trivial canonical bundle. And for instance, there is a criterion for almost abelian Lie algebras admitting non-zero holomorphic and zero forms given by Fino and Paradiso. Recall that an almost Lie algebra is basically one factor is 0 acting by the adjoint action in an abelian ideal U. So they gave this criterion, but also we can recover their criterion using our characterization. And also we can produce new examples. For instance, if the Lie group admits an abelian complex structure, this is that the bracket of Jx and Jy is equal to the bracket of Xy, and the group has a lattice, then the submanifold has trivial canonical bundle because this satisfies our condition in the characterization, the condition in our characterization. So we have examples of 2n-dimensional complex submanifolds with an abelian complex structure having a trivial canonical bundle, and also we have some examples in some almost nilpotent submanifolds, always via a invariant trivializing section. Let me show you now an example of a complex submanifold with the non-invariant section of its canonical bundle. We start with the 4-dimensional Lie algebra, E0 acting on the Heisenberg 3-dimensional Lie algebra, rotating the factors. So one can define a complex structure, J on G, defining sending E0 to E3 and E1 to E2. But this complex structure does not admit a close to 0 form, since the Kosul form psi is equal to minus 2 E0, so it doesn't vanish. However, one can produce a section of the canonical bundle, noticing that the associated simply connected Lie group G is diffeomorphic to R4. So in coordinates T, X, Y, Z, we have exactly that this E supra 0 is equal to dt, So if we consider this to zero form tau given by the left invariant to zero form multiplying by the exponential of it, then this factor is like it corrects and give us the closeness of the form tau. And we have that the Lie group G admits a lattice gamma of this form, which in the first coordinate are integer multiples of 2 pi. So by this reason, the form tau is gamma is invariant by the action of gamma, since the exponential of e multiplied by integer multiples of 2 pi is equal to 1. So we have this invariance. So we can descend to the quotient, this form tau, and therefore we have an over-vanishing close to zero form on the corresponding solvmanifold, saying that this solvmanifold has trivial canonical bundle, even though it does not admit an invariant section. Okay, another way to see this, just to remark, is this solvmanifold is actually biholomorphic to a complex nilmanifold, where coming from the direct product of R and H3, and here J tilde is induced by a left invariant complex structure on the group, because this gamma is a lattice both in G and R cross H3. So by Mostow theorem, yeah, okay, we have a biholomorphism. Okay, what about the canonical bundle? We are looking for non-invariant sections. What we proved with Adrián is, if we stay at the level of the Lie group, the canonical bundle of a simply connected solvable Lie group with a left invariant complex structure has trivial canonical bundle, but probably this nowhere vanishing closed and zero form maybe is not invariant. In any case, an over-vanishing section of the canonical bundle can be written as a product of a smooth function and a non-zero left invariant and zero form. But the problem is that if we have a lattice, the section we construct in the theorem may be not invariant by the action of the lattice. So this is why there's so many, not all, of course, not all complex and manifolds have trivial canonical bundle. But there are obstructions for the triviality of the canonical bundle. For instance, it is well known that if a complex manifold in general has trivial canonical bundle, then its n Betti number, so the middle Betti number, has to be greater than or equal to 2. But we exhibit an algebraic condition in terms of psi for the canonical bundle to be trivial, and this is the condition. If we have a simply connected Lie group, not necessarily solvable, can be any simply connected Lie group with a left invariant complex structure and a lattice. If the complex manifold has trivial canonical bundle, then the Kosul form psi must vanish on the commutator, or equivalently must be closed. The sketch of proof of this is very nice proof with many facts. Bezzoni proved that the two form given as in the theorem called rho is actually the Chern-Ricci form of the Hermitian manifold for any left invariant Hermitian metric. Then, using a result by Tosati that if the manifold has trivial canonical bundle, then this Chern-Ricci form can be written as I del bar of some smooth function. And to finish the proof, we use the Belgun symmetrization process to obtain left invariant objects. So we symmetrize this row, obtaining, since the symmetrization commutes with the Dolbeault operators, we obtain I del bar f tilde, but since f is a function, f tilde, the symmetrization is 0. So we obtain that this row tilde is 0, but since we start with row which is left invariant, the symmetrization coincides with row. So we obtain that the Chern-Ricci form is 0. So this tray of J at the bracket is 0, and we obtain the condition in the theorem, which is a nice algebraic obstruction for the canonical bundle to be trivial. As an application of that, we can say something about compact semi-simply groups. Well, in the 50s, Samuelson, using roots, proved that...
Alejandro?
Yes.
So, is also an obstruction that the first Chern class is 0? Or what's the relationship with the first Chern class?
Yes. Yeah, the canonical bundle is...
if it is trivial,
implies that the first Chern class is 0, I think.
Okay. And the converse,
I think in the article of Tosati there are examples that no, it's not true. It's
okay.
Like the condition of first Chern class 0 is too weak.
Okay.
Also, I think there are examples where the canonical bundle is not holomorphically torsion, so even neither a power is trivial. So yeah, it's only one direction. Okay, thank you. So as I was saying, for every 2n-dimensional compact Lie group, Samuelson proved that it admits left invariant complex structures.
Alejandro?
Yes.
I think there's a question from Roberto.
Okay.
Raise his hand.
Can you read it, please?
I think, Roberto, do you want to switch on your mic?
Okay.
Yeah, okay. Yeah, I wonder about gamma. The result does not depend on gamma?
No, the result does not depend on gamma.
Okay.
Because it's for any left invariant metric, so it's a condition only in the Lie algebra.
Okay.
Okay, thank you for the question. Well, so every 2n-dimensional compact Lie group admits left invariant complex structures. Samuelson proved this using roots, and then Petty later, 30 years later, proved that every left invariant complex structure on a compact Lie group is obtained via this Samuelson construction. And using this obstruction, I told you a slide before, we can prove actually that the canonical bundle of a compact semi-simple Lie group with the left invariant complex structure is not holomorphically trivial. We can give a proof of this. I think this fact was well known, but anyway, it was nice to have a proof of this. The sketch of proof goes like this. Since it's semi-simple, the commutator is equal to G, so it suffices to show that the Kosul form doesn't vanish for some x in the Lie algebra G, or, which is equivalent, the trace of the complexification of J multiplied by add x is not 0 for some x in the complexification of G. And one can see that using Samuelson's construction, there exists some element H in a Cartan subalgebra HC, such that this trace does not vanish. So we are done, and the canonical bundle will not be holomorphically trivial. But okay, what about if rho is equal to 0? Well, of course, this condition does not imply that the canonical bundle of the complex manifold is trivial. For instance, consider the Lie group that I talked in the previous slide, the example with the left invariant complex structure considered the ring. So as the Kosul form has only a part on E0, it vanishes on the commutator, but the Lie group G admits a lattice. Now, in the first coordinate, there are integer multiples of pi, such that the corresponding complex manifold is a secondary codira surface. So it is well known that it has non-trivial canonical bundle. So this condition is far from being sufficient, but in some cases, we could produce some non-invariant trivializing sections of the canonical bundle that I will summarize in this proposition. So assume that you have a 2n-dimensional simply connected solvable unimodular Lie group with a left invariant complex structure, and assume that psi vanishes on the commutator. So the kernel is an ideal and a codimension 1 ideal. So we can write G as this RE0 acting on the kernel, and consequently the simply connected, well, the group G can be written also as a semi-direct product, where here H is the unique connected normal subgroup, such that the Lie algebra coincides with this kernel, this ideal. And then we can produce an N0 form, which is closed by multiplying sigma, which is a left invariant N0 form, by this function related to the psi in E0, and here T is the coordinate of R. So let me show you an example of this proposition. We have this almost abelian example. Is a one factor acting on the abelian ideal R5 with this matrix, which has some rotations, but also these two ones here. And the R5 is spanned by E2 up to E4 and the E6. We can define, as usual, this complex structure, sending E2 to E1 to E2, E3 to E4, and E5 to E6. One can see that the Kosul 1 form is not 0, but it vanishes in the commutator. So as in the proposition before, since we have this 4 here, now the function we multiply is exponential of -2 by I by t, and then it is a closed 3-0 form, but we can produce a lattice compatible with this function. Indeed, the exponential of pi multiplying by the matrix A is equal to this matrix, which taking the Jordan form, we can see that it is conjugated to this matrix, which is integer. So using Yamada's result, we can say that G admits the lattice gamma, which is given by this factor pi, multiply the integer multiples of pi, acting on P set 5, where P is the matrix which conjugate this matrix, the exponential, to this matrix B integer. And by construction, the form tau is invariant by the action of gamma, since now we have these two. So again, we use the periodicity of the exponential. So we can descend this closed 3-0 form to the quotient and obtain that the canonical bundle is trivial. And again, with the non-invariant trivializing section. And for instance, in this case, this gamma is not the lattice of an nilpotent Lie group, since every lattice on a nilpotent Lie group is nilpotent. But here, as the lattice comes from an almost abelian Lie group, it is easy to compute the lower central series. And as this matrix B minus the identity is not nilpotent, this central series do not vanish, so it's not nilpotent. And thus, this complex manifold is not bi-holomorphic to a complex nilmanifold. And to finish, I would like to give an application of these solvmanifolds with trivial canonical bundle via non-invariant sections to hypercomplex geometry. I will recall briefly some about hypercomplex geometry. A hypercomplex structure on a smooth manifold is a set of three complex structures, J1, J2, and J3, such that the laws of the quaternions are satisfied. J1 and J2 anti-commute, and okay, and we define J3 as the product of these two. If you have a hypercomplex structure on your manifold, this implies that the dimension of the manifold is a multiple of 4, since one has this action of the quaternions on each tangent space. And well, every time you have a hypercomplex structure, in fact, you have a whole S2 sphere or of complex structures, because for any point A equal to A1, A2, A3 in S2, you can define this sum of n, you will have a complex structure. And a very interesting object arising in this context, which is the Obata connection, because if we have a hypercomplex structure, then there exists a unique torsion-free connection, nabla O, such that the three complex structures are parallel with respect to this connection. And it is known as the Obata connection. And a nice formula was proved recently by Soldatenkopf in terms of the bracket J1, J2, and J3. So since the complex structures are parallel with respect to nabla O, the holonomy of the Obata connection is contained in the quaternionic general linear group, which for this talk we will define as the matrices of size 4n in R, such that they commute with the usual hypercomplex structure on R4n. And it is interesting to consider not only when the holonomy is contained in G, in GL, but also in SLNH, which is the commutator for us of the quaternionic general linear group. So in this case, if the holonomy is contained in a special linear quaternionic group, then the hypercomplex manifold is called an SL-NH manifold. And these are studied by a lot of people recently. And about them, Misha Verbitsky asked a question. He proved that if the hypercomplex manifold is SL-NH, then the complex manifold with respect to any of the three complex structures has holomorphically trivial canonical bundle. And he asked if you have a compact hypercomplex manifold and assume that the complex manifold with respect to J1 has trivial canonical bundle, does it follow that the holonomy of the Obata connection is contained in SL? Well, this is true, for instance, if A admits an hyperker with torsion metric. This was proved by Verbitsky himself. And also, for if another case, which this question is true, is when M is a nilmanifold with an invariant hypercomplex structure. This was proved by Barberis, Dottin, Verbitsky. And well, the question is what happens with hypercomplex solvmanifolds? Okay, so if you have a hypercomplex solvmanifold such that the canonical bundle of the complex solvmanifold with respect to J1 has a left invariant trivializing section, then the same proof works as for nilmanifolds. So in this case, we will also have that the holonomy of the Obata connection is contained in SL. The problem, of course, is when this canonical bundle has a non-left invariant trivializing section. And with Adrián, we constructed an example of an 8-dimensional hypercomplex solvmanifold such that the canonical bundle with respect to J1 has a trivializing section, which is not left invariant, and it is not an SL-NH manifold. So I will finish by showing you this example, this nice example. So we start with a 4-dimensional, completely solvable Lie algebra, E0 acting on the Heisenberg Lie algebra, and now the action is diagonally. It's diagonal, sorry. Well, we can define a complex structure on this Lie algebra. But here, the interesting fact is that G plus and G minus, which are E0, E2, and E1, E3, are subalgebras of G. And this is a too strong condition because by a result by Andrada and Salomon of 2006, this implies that the realification of the complexification of G, which I will call G hat, admits a hypercomplex structure, J1, J2, and J3, where J1 is given by multiplication by I in the positive part, let's say, and multiplication by minus I in the negative part. J2 is the extension of J to the complexification, and well, J3 is the product. So setting Fj equal to I times Aj, and taking this basis, we see that these J's have this nice form. And well, we have also the Lie brackets. Basically, we have this E0 acting on, and also this F0, both are acting on the complex 3-dimensional Heisenberg Lie algebra. E0 is acting diagonally, and F0 is acting by rotations. So we can use Yamada's result. This H3 is the nil radical of G hat. the corresponding simply connected Lie group. And we can produce a lattice, gamma m, for each m greater than or equal to 3 of this form, which is an integer multiples of Sm plus integer multiples of pi. This pi here is important, plus a certain lattice on the nil radical. So we can, yes, and here it appears this logarithm, which is a number which appears constantly when we are working with lattices. So in this case, if we call psi alpha to the corresponding Koszul 1 forms for each complex structure, then none of them vanishes. So there are no left invariant trivializing sections of the canonical bundle of any of these complex solvmanifolds. And also, as F0, sorry, as E1 and F1 are in the commutator, our abstraction says that the canonical bundle with respect to J2 and J3 is also is non-trivial. But, however, we will see that with respect to J1, the canonical bundle is trivial. Indeed, in real coordinates of the group, because we had this pi, we can multiply the closed 4-0 form, this form, left invariant, by the exponential of 2 times I times x2, and we obtain a closed 4-0 form, which is invariant by the action of the lattice. So we can descend this form descends to the quotient, and the complex solvmanifold with respect to J1 has trivial canonical bundle. But this example is not an SLNH manifold, since due to what Verbitsky proved, the canonical bundle of all complex structures must be 0. But in this case, with respect to J2 and J3, they do not have trivial canonical bundle. So this example provides a negative answer to Verbitsky's question. And the final remarks, in Gentili-Tardini, they proved that a hypercomplex solvmanifold is SLNH if and only if the canonical bundle of the complex solvmanifold with respect to J1 admits an invariant trivializing section. So, so this was exactly what which fails in our example. And okay, so the Verbitsky's question remains open for a hypercomplex manifold in which the complex manifold has trivial canonical bundle for all alphas. And that was all. Thank you for your attention.
Thank you, Alejandro, for this talk. Well, now there are some minutes for questions or comments.
I have a question. I don't see what's the difference between holomorphically trivial and topologically trivial? Topologically trivial is C1, 0?
No, topologically trivial, sorry, because all the solvmanifolds are parallelizable, so they are trivially topologically trivial. So the question here is this: we are considering the all holomorphic, so we want a holomorphic trivializing section.
Okay. Because in this paper by Grancharov, in the compact case, in the homogeneous compact case, in these T spaces, Grancharo characterized what is to have a zero first Chern class. Is it known a characterization for holomorphically trivial bundle in those spaces?
I think that no, that there is no
characterization.
No. It's exactly what we are looking. There is not known a characterization of manifolds, of complex manifolds with a holomorphically trivial canonical bundle.
No, but I mean in these C spaces are very special. Homogeneous, compact, homogeneous, complex manifold.
I don't remember.
Grancharov gives a characterization of C10 in terms of the Kosul form, also restricted to some torus.
Okay.
But do you know is there anything known about the canonical bundle there?
I don't remember. I would have to read this paper of Grancher, but I think no.
I think that means that the power of the canonical bundle is trivial, but I don't know if the canonical bundle itself is trivial.
What? The C10 or the
Yes,
topology?
the C1 equal to 0.
Okay. I see. Okay.
Yes, but sometimes it's difficult to distinguish between trivial canonical bundle and a power of the canonical bundle being trivial. It's not so easy to verify that.
Yeah, I don't know. Because I remember this Tossati's paper. I think the condition C1 equal to 0 is too weak. I don't know. I will look because I think that there are examples of complex manifolds with first Chern class 0, but the canonical bundle is not holomorphically torsion.
Okay.
Isn't it the case that if you have if you have trivial C1, then there is a Ricci flat representative, right? At the Riemannian, at the Kähler sort of level, right? This is one of the various definitions of Calabi-Yau, right? You will have a Ricci flat representative in that Kähler class. That's Yau's theory, right? And then doesn't that give you a trivialization, a holomorphic trivialization of the canonical one?
No, but that's
sorry, I couldn't understand.
The Calabi-Yau theorem goes for Kähler.
Right. Yes. So, I see. Right. So in the sort of
Kähler manifold.
Right. So you in this sort of non-Kähler setting.
Yeah.
Yes.
But still, yeah.
Okay. Is there any other question for Alejandro or some comment? Alejandro, do you have an example of a solvmanifold which is completely solvable and has trivial canonical bundle? Not less invariant.
No. Yeah, left invariant section, you mean?
Yes, less invariant section.
No, for the completely solvable case, there are a few examples, and these examples is like they are showing that if a completely solvable complex solvmanifold has trivial canonical bundle, must be an invariant section, but yeah, this is the picture. We don't have a proof yet, but
like the same as in the nilpotent case, you mean?
Yes.
Okay. Okay. Well,
it sounds like a theorem. Huh?
Yes, but yeah, we don't have the proof, just some evidence. But there is not.
Because in that case, it will never be a nilmanifold also, right?
Yep.
Yes. Yeah, we have. I am like looking at all the unimodular solvable 6-dimensional Lie algebras to find in which we can obtain this trivial canonical bundle by non-invariant sections, and well, maybe that we can find more evidence, and yeah.
So in dimension 6, there is no completely solvable ones with.
Yeah, probably.
Okay.
Yeah. Also, yeah, there are more open questions related to this.
Okay. Well then, is there any other question for Alejandro? Well, if not, let's thank the speaker again.
Okay, thank you.
Well, and thank you very much, Alejandro.